Welcome to Clinical EEG, Part 1, the normal EEG of the adult. Shown is a 10-second epoch of a normal EEG, as typically assessed by a clinical neurophysiologist. Total duration of routine EEG recordings is typically about 20 minutes, and I will explain later about the various elements of such a recording. First, it's good to know that as brains are spatially inhomogeneous, both regarding function but also in the generation of rhythms, we typically use a spatial sampling of brain rhythms. This means that we don't use a single recording, but we record rhythms from different parts of the brain. And that is illustrated here. So if this is the skull, then for a normal routine EEG recording using 19 electrodes, these are spatially homogeneous, attached to the skull according to the 1020 system. You can look in the books what that means. In essence, it relates to percentages of the circumference of the head to make it spatially nicely sampled, with sort of equal distances between the electrodes. Another thing to note is that we use a combination of letters and numbers, and odd numbers relate to the left side of the brain and even numbers relate to the right side of the brain. And in addition, we use FP1 or FP for frontal polar, F7 for frontal, C3 or C I should say for central, T for temporal, P for parietal, and O for occipital. And in the midline we have frontal Z, central Z, and parietal Z. So this is the nomenclature to indicate where a particular electrode is placed. And if we record brain rhythms as we will measure voltages, we typically need at least 2 electrodes. And what is shown here is a bipolar montage where we measure the voltage difference between 2 electrode positions. You can compare this to standing on a hill, and the height of your hill is estimated where the reference is another hill. So it's a relative measure of height, and in this case the voltage difference is a relative difference between 2 electrode positions. This is a very common montage, and what is shown here is actually a double banana, because we measure the voltage difference between this one and this one, which is FP1, F7, or between this electrode and this electrode, which is T3, T5. And between this one and this one is F7 minus T3. So in this way we can record 4 voltage differences on the left side, and similar on the right side, and between this one and this one, this one and this one, this one and this one, etc., on the left and on the right and in the central. So that eventually results in 19 traces. And then, of course, you have to define how to display that on the screen. This is a very common way to do it, where we display the first 4 bipolar recordings from the right hemisphere on the top, and then the similar one from the left side below. And then these are the more central located time series recordings, and this is on the right side and this is on the left side, and this is central. And immediately note that the time series are different. Over the frontal regions, the amplitudes and the rhythms are different, for instance, than over the temporal and occipital regions. So there is a spatial gradient. And at the same time, you may appreciate that it is quite symmetrical. This is right and this is left, and this is again right and this is left. So left and right hemispheres tend to generate quite symmetrical rhythms in physiological conditions. So this is the indication of where this particular trace was recorded from. And on the right, we see the sensitivity. So this distance is 50 microvolts. And typically for all the channels, we use the same sensitivity. So these wiggles have an amplitude of about 50 to 60 microvolt. We can also calculate the frequency, because this is always 1 second between these bars. And this is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's about 9 to 10 hertz that is shown here. And there are some slower waves as well here, but in general, this whole recording shows rhythms in the alpha range, which is between 8 to 13 hertz. I will come back to that later. Before we discuss the details of the various rhythms and their meaning and the various rhythms that we can observe, it's good to note that the way the electrode is attached to the skin and the quality of the electrode is also of importance. If this is not done correctly, artifacts may occur and part of the signal may be distorted. So you need good material and a good lab tech. In fact, there's a lot of literature on the non-trivialities associated with this process that's outside the scope of the current screencast, but more details can be found in the reference. Now, one more aspect before we go to the rhythms relates to what we mean with negative and positive. We are measuring voltage differences. So what is it if we mean negative or positive? In fact, as we are measuring differences, we can only state that a particular recording position is more negative than another one or more positive than another one. The convention is as follows. In this example, we have shown a recording at or between C3 and P3 and another trace between P3 and O1. Now, the convention is that if the curve bends downwards, as indicated here, that at that particular moment, the electrode to the right is more negative than the electrode to the left. So at this particular moment, P3 is more negative than C3. If the curve bends upwards, then it means that the left part of the electrode is more negative than the one on the right. So in this case, P3 is again more negative than O1. So that's the convention. So you could also say it points, if you consider this a direction, downward to the right electrode, and it points, if it goes upwards, to the left electrode. And pointing to means that that particular electrode is more negative than the other one. So illustrated with charges. So these are the same three positions as we just discussed, C3, P3 and O1. And now the charges are indicated. So say that at a particular moment there's more positive charge near C3, more negative charge near P3 and more positive near O1. If we have this bipolar recording, so this channel reflects the voltage difference between C3 and P3, this recording between P3 and L1, then as indicated here with the red rectangle, at this particular moment P3 is more negative than C3, and that's why C3 minus P3 points downwards, as was indicated here. And P3O1, which is the other trace, it reflects upwards. That means that P3 is more negative than O1. So using these two electrode positions, you can basically argue or state that most of the negative charge is present around P3 in this case, at this particular moment. And this will become relevant as we will discuss phase opposition, actually negative or positive phase opposition, in relation to the networks that, for instance, generate epileptiform discharges, where we are really interested in where this particular location is approximately in the brain.